and as a result, some of the output is very unexpected. You don't get what you're expecting, you don't get what you want, but you get a lot of input from this into what directions you could go in. We did a bit of that with the robots. So this is us saying, I have 3 robots, can I form this shape? So rather than going through the whole process of simulating cutting metal, setting up the robots, we just say, well, just try it and get 3 contact points. So normally when you fold something, you sort of work your way along it slowly and get it folded, but that doesn't happen with the robots. You've got to be able to just take 3 points and just do the whole thing simultaneously. So it's quite quick to just test if that's possible too. And these sorts of things are small scale, they're really rough, there's no cost for making a mistake, and we kind of encourage making in this way at early stages, because you shouldn't be trying to make something perfect. You should be happy to make some mistakes. So we bring that into our software, which will do things like let you change the fold angle, the scale, the positions of these and stuff. And if you get to a point that you're happy with, you kind of pause it and we say, okay, well we'll make it at that particular point in time. And we have a little desktop vinyl cutter, so we can quickly make some clean models from that. And then we would take that into our CAM software. So we'll sort of set this up for our router to cut everything out. So again, we've developed our own software so that we can basically deal with many sheets, sort of hundreds of sheets. Normal CAM software does require you work through objects one by one, setting everything up. You go to the next object and set everything up again. And in this case, if you set everything up for the router, you could change your design and not have to set everything up. So we don't have this sort of linear process of design something, finish designing it, start getting ready to manufacture it, finish manufacturing it, and install it. All of those things are parallel. So we might be installing something and someone may change the design and it updates our CAM file, which will generate new code and will cut new parts and continue the installation, and the final design has changed, but we'll carry on making it if it's still compatible. So this is very non-linear. It's pretty necessary in today's fast-paced world of short deadlines, as you've experienced with your 4-day deadlines. I mean, it's just what happens. You have to be able to deal with it. So it's quite normal, really, I think, to work this way. Yeah, and then we just get that to generate the code and make some parts. Let's have a look at a little video. So we then set up our simulation here. So this is just a model of our workshop. We have a couple of robots in this space. And here you can see how, I guess it gets quite difficult, you could say, to actually set these robots up so that they're actually forming these parts. But it's quite, you've got just a couple of vacuum grippers here, so they just suck themselves onto the metal. This is a plastic coating, so there's no kind of harsh impact on the surface, so it stays clean. We can peel that plastic coating off when we get to site and install it. This is it, sort of half installed. So these are all quite large scale. So we found, from developing this technology, developing the processes and software. We have a few different areas we can address now that aren't purely Robofold technology. Design and development for projects, design consultancy, workshops and training. This is something we did for Foster and Partners recently, looking at how we could do a window shade for a building, but it was an elliptical building, and as they went around the building, the sun angle meant that this kind of shade here, it needed to get smaller where there was less sun and bigger where there's more sun, depending on that curvature. So we linked that to the way the building was curved, and this would just get, this would change shape in the model according to the sun angle. And this is formed from a single piece of metal that forms a box section. So it's easy to say, okay, well, it changes shape, so we just weld different bits together as it goes round, but we have made this from a single piece, so two sort of double skin as well, so it was kind of a bit more complex. And in this example, it's just a straight, flat piece of wood, but in their building it's elliptical, so in order to follow that, this had to curve as well to get around the building, so it got a bit more complex. Some details of that. And some of the examples. So these are all just varying. So as I said before about these, say a single piece to us is actually, it's varied by some of the parameters. So like this corner condition here changes as you go around. But essentially it's just the same piece to us, really. And yeah, we started developing the software, like the CAM software to run our routers, and now we're developing some robotic software. So we've had to develop robotic software to make our robots work, but it would be impossible for anyone to use that robotic software. So we've kind of wrapped it up in something more practical for people who use Grasshopper and Rhino. So this is a visual programming environment. So people familiar with CAD software, you can basically use this environment to drive the CAD software. So here we have a robot simulation, and this is just saying move this robot along a path in space, and these are the positions in space. Here's my robot, here's my grip on the end. So rather than writing many, many lines of code to create this, you can kind of plug stuff in together and get a simulation of a robot very quickly. Some more images here. This is sort of indicating that the robot has gone into a zone where it's clashed with another robot or the environment. So it's getting quite technical but it shows kind of what we've had to do in order to get this technology to work. It's not just create the output, but the back end behind all of this to make it work. So it's been quite complex. Okay, so that's kind of it. I think, yeah, you've seen quite a journey there of where it started and how the technology works, the types of applications that are possible, but also what's behind the scenes is that we've had to create a lot of software and do a lot of work to create a technology that is just emerging, really, and there are a lot of parallels there to the world of 3D printing, which has massive amounts of input, but in a similar way, is still just emerging. So there's paper here if you want to have a go. But otherwise, thanks a lot.
So we've got questions for Greg. Thoughts?
I've got two cheeky questions. One is, When did robots come into the whole design principle? Was it right on? Was it right at the very beginning?
No,
robots who do this.
It was at the end, I guess. It was about 5 years ago. I was just trying to make machines to make this, and because I had this goal of industrializing this folding process, and yeah, I sort of started making machines and realized that I would have one machine for one shape, so I have to build another machine for another shape, and then, well, why don't I just like CNC machine some tooling if I was going to make one thing for one shape? So it seemed pointless to go down that route, so I had to find something that could follow these sort of complex paths in space, and the robot was the only thing that could deal with this sort of spatial, deal with a spatial type of process. So yeah, it ended up, it wasn't startup robots, it was the best tool for the job, really.
Second question, and I've probably got asked this all the time, is what's happened to the bike?
Yeah, I haven't finished making. I haven't finished this thing. I haven't finished the process yet. Bikes are quite, they're quite advanced in a way. I mean, the bikes that I've been riding are sort of aerospace quality aluminium. They're all CNC machined and robot welded together. So, yeah, the technology hasn't reached aerospace quality yet. So when it does, I'll make a bike, I think. So yeah.
What do you use to score the metal?
We use a CNC router, so we just cut through 50% on the reverse side. The same way I score through it, 50%, we just cut through. So it just provides a natural fault line. So when the robot moves, it just wants to fault along that line, basically. So it folds in the right place. So it's quite easy to do that with, say, a laser cutter on paper. You just sort of do a dotted line, or you can do that with a laser cutter on metal. You can do a sort of dotted line. So it's known technology in terms of how to fold metal or other materials with low force. So rather than using a brake press to fold something in a straight line, you can then fold something by hand in a curved line or with a robot.
I write software, which is often quite thankless task. I'm enormously impressed that you've taken what's a kind of craft-based, non-deterministic starting point in the process of creating the software and assumed that you'll make it good, rather than come from a software starting point. And you've made that so functional, I think is very impressive.
Yeah, I mean, it's had advantages as well. We just had a grant to look a bit further at the spring back of metal.
Yeah.
And we could have just like spent the same amount of money on some FEA software that was predicted the spring back.
Yeah.
But to us, it was more interesting to be able to model it in real time, basically. We don't want to wait 2 hours for a really good answer. We'd rather not wait any time for an okay answer, which gives us an indication of what we need to do to get a really good answer. So it's much more useful. So it's meant that the particular way we model this is, basically break this up into lots of flat faces. So it's very coarse representation, but it means that we only have to do calculations on like tens of elements rather than tens of thousands of elements, which is finite element analysis. So we can do it in real time.
Very impressive.
Have you ever done any of this with kids in school?
Well, I don't know how. Yeah, university students, nothing younger yet.
I can see 14-year-olds really loving it.
Oh, yeah, like
loving
kids
the
do,
paper
yeah.
stuff, right?
Yeah.
And then the question for me is, what could they then do with not very stiff metal? Because it would be